plate, so the internal structure, the fins or pins of a cold plate for the cooling of 3 IGBTs. First, I give you an overlook over the model. Then I show you or explain you the project definitions roughly. And for those of you who don't know FloEFD, just quickly something about the mesh because it is kind of important part of that. I give you also a quick live demo of the parametric study, and then also explain the results that I got from it and the summary of what we've learned. This is the model that I used. There's a cold plate in that. We have the 3 IGBTs that were provided from eCooling, Mr. Segon. You can see the IGBT's interior. You have the IGB chips, 4 of them in one module, and 4 diodes. These are the fins of the cooling, which I will change in numbers and sizes. And just a quick look on how detailed the IGBTs are. So we have the silicon, we have the solder, copper, ceramic plate, we have another copper layer, solder or tin material, the base plate, and then a small thermal resistance as a tin material to the cold plate. So we start with the triple IGBT module on the cold plate. We can change the fins and pins in shape and size. The cold plate is just simple aluminum. You can change the material if you like, but that's just for the demo, as well as it's just water as a coolant, so no special coolant liquid. The IGBTs altogether have, the IGBT chips have 690 watts, so 3 of them with each 4 chips. So per chip, it's about 57.5 watt per chip. For the diodes, it's 480 watt or 40 watt per chip. And the IGBT module consists of various materials, as you've seen in the structure. And I only use the local mesh for refining the region where the fins and pins are in the cold plate, as well as for the IGBTs in order to, well, get a little bit finer mesh on the structure of the IGBT. So in this parametric study that I used here, I can basically change the fin length, the fin thickness, the spacing, and the pattern are defined by equations. So if my fin gets longer, I have to have a bigger distance between them. Otherwise, if it's just very small, I can have one long one. It doesn't really matter. So there's some kind of equation behind it automatically rechanges that. You can go into more detail, make it more advanced in the equation. I just put a factor in there so it gives a little bit of a gap in there. What you also can do is you can change the flow rates, you can change the coolant temperature. For example, if you have a cold start or if you're driving for a long time, the coolant is not 20 degrees in the inflow, it's something around 40 to 60. You can change the fluid, of course, gases or liquids. You can cool it with air, of course not that efficient. And the cold plate material, of course, you can do it copper, but then it's getting more expensive. The channel height, so the width is, well, about the size of the IGBT, so it doesn't really matter if it makes it any bigger. But the height to get more water through or to squeeze it for higher velocity through the channel. The width, the length. The pins instead of the fins, because in my study I just use the fins. I can simply switch it by activating, deactivating the other part, and then run the same amount of variations in there. You will see it in a second. They both are linked to one parameter, so if I change that parameter, both will change in sizes and also the distribution. And of course you can also use other shapes than pins and fins. You can have like ovals or whatever. For the setup, well, the model setup took me less than 15 minutes. It was more like hiding the components so I can get to the layers in the IGBT to apply the material, or finding them in the tree of Catia. And that's basically it. The parametric study, I simply define which values to change, and then it basically runs through all these values, creates automatically all the projects that are possible, all the combinations. So the mesh size for the finest fin model was about 2.5 million cells. it took me about 9.5 minutes to mesh the model. And the one for the coarsest fins mesh with a much larger distance between the fins was just about 600 cells with 1 minute 15 seconds to mesh. And that's the important part. The meshing technology, it is a Cartesian mesh for those of you who don't know it. Cartesian mesh, you would think like, okay, you get stair steps in the geometry if it gets too complicated. But here comes the immersed boundary layer into play. So if I have anything angled or with a fillet or any more complex, you have the partial cells which are part solid, part fluid. So this is the fluid area, the area where the flow enters here. You see here one fin, there's another fin, and that's the aluminum casing of my cold plate. And also we apply a special wall function because you probably have seen that there's very rough cell size. If you know about traditional CFD meshing tools, you resolve the boundary layer in that way. So we have a special wall function that takes into account if we don't resolve the boundary layer, if we resolve it with the mesh. If we resolve it, we calculate it. If we don't resolve it, we have a wall function that basically, the boundary layer model is pretty much detailed and researched, so you can apply certain equations in order to work with the heat transfer, friction, and so on. Let me get to the demo. So this is my model. You can see we have the IGBTs on top, so I'm going to hide them. This is my top part, and the lower part, this is my top part of my IGBT cooler. And you can see here, both of them are still shown. So you can see here the pins as well as the fins. They're two separate parts, so I can activate, deactivate them with the parameters. Now, I have a set of parameters here which Catia can provide. I don't know if, I'm not that familiar with NX and ProEngineer. We have colleagues where they're much better in that. You probably can define similar tasks there. So these parameters are in the main product, and I made them public in order to access them and change them. So all the parts which are in some way related to this parameter are linked to that. So in an equation, if it says 2 times the fin size, it will use the parameter. If I change it here, for example, fin length, it only affects now the fins because the other ones are radius or round. So let's do, instead of 10, let's make 20 millimeter. So it gets red, I have to update the geometry. And you can see it automatically changes. If I change the thickness from 2 millimeter to, let's say, 4, you will see that, for example, also now the pins will change because they refer to the thickness as their radius. So, of course, 4 millimeter radius would be an 8 millimeter diameter then. And update, now both are red, so we have to update it again. We'll see how that pattern automatically changes. So it really goes only from that edge to that edge, and from these boundary areas here to the other ones. And depending on what I set, the changing, the shapes and the amount of fins I create will change. The finest one was 1 millimeter, and for the length we had 5 millimeter. So if I update that, you will see it's very, very fine. And you will see later in the results how that will behave then on the flow, on the temperatures and so on. So with this, you basically can reproduce any geometry. You can change anything. You can create kind of porous matrix. There's some kind of mixers who have diagonals, rods to each other. You can place these things. If you place it once, you can pattern it. You can change the dimension of the diameter of these rods, and this way you can really create your own structure here as you like it. Now these parameters are basically what I'm going to change. So let me switch to another project where I already have that defined. almost there. Here. So this, you can see it's the same assembly. In this case, I deactivated the pins. So you can see a small bracket here that tells in Catia that it's deactivated, the component. I included here a design table. In this design table, I referred to the parameters that I might be able to change. So this design table I can control from the parametric study. Now, in this case, I cannot control the parameters here anymore because they're fixed by the design table. I would have to go into the design table and change it there. So that's why I showed it before, where I can still easily change them. So the parametric study is here in my project. You can see your parametric studies, and I named it fin study. So let's go in here. Here you can see several of the parameters. You have the fin length, you have the component activation state for the pins. No, that's the fins. That are the pins. It's just a Boolean value. 1 is active, 0 is deactivated. So that's why the pins are not shown. You have the pin or fin thickness, the diameter or the thickness of the fins. And for example, I can also change the volume flow rate. Or if I like, just add another parameters for the volumes. Let's say boundary condition, inlet volume flow, temperature. Click OK, and I have a temperature in here too. And I can change, for example, the temperature, make that from 20 to 60 Celsius for the inlet in, let's say, 5 Celsius steps. Okay, you see automatically it creates all these combinations. As soon as I click on scenario, it will create all these I have to update that. You will see how the bar slides down because it creates more and more and more to the right, more and more combinations. Here you see all the parameters that I have chosen here, and they will add another one for the temperature. And the more you create, of course, the larger gets the matrix. And now we have, I think, like 6 parameters, 4 for the length, 4 for the diameter, plus again 5 or 6 for the temperatures. So it's a huge matrix that it's now creating. But as long as I have enough time, or if the model is small enough, I can still run it just in series. Or if I have enough solver licenses, I can run them also in parallel if I have enough computer to just distribute it on the other computers. Here's my matrix, and you can see it's really huge. It goes up to 108 design points. So other parameters that I want to know are, for example, my goals, such as that's the solid temperature for average and maximum of my fins, the IGBT minimum, average, maximum, as well for the diode min, max, and average. I have my delta temperature from inlet to outlet, as well as delta total pressure. So I know exactly what pressure loss I have. I can also add some post-processing plots, which I already have defined in advance, so which layer and so on. And if I go to the plots, then here, it will update the images as I calculate. The same goes for surface plot, or in case of my goals, takes a second. You will see for each of these, the goals, I can change them into a chart where I have then bar charts. You can see how they compare to each other, if it's higher or lower. And of course, I can also export it to Excel and work from there in more detailed graphs and so on. So at this point, I would basically then say, okay, that's my scenario. I can run it or also allocate different computer to each scenario and then just start the calculation. If someone uses FlowMaster here, you can also then use these basically characterization of my cold plate. If you have a fixed cold plate, you want to drive different temperatures and volume flow rates, you can use it in order to characterize it and put it into a full cooling loop in a car or airplane or wherever you want to apply it for valves, pumps, or whatever. This way, you get kind of a characterization of a 3D component which you can plug into one system simulation and run through all the variations in temperatures. Depending on how the system behaves, it takes the actual parameter of the component in the system simulation. Okay, so Done with that. Now let's have a look on the results that I created, not for this huge model. So my smallest mesh was this. It has enough cells over the distance here as well as between them. And my largest mesh was for this one. You see all these small white dashes in here? Those were the fins of my model that I showed before. So design point 2 and 10 were the two like extremes. Design point 3 is very similar, just a few more cells, but it has the lowest temperature, the highest temperature. This is my IGBT mesh. You can see here's part of the fluid in here as well as around it. And if I zoom in this area, you can see the structure of the mesh. You have here, that's a copper layer as well as this one. The IGBT chip here in that case is in a plane further behind, so you don't see the IGBT chip, but you can see then the ceramics here. You can see another copper layer and very thin the solder or tin material. You don't really have to resolve in the thickness because the partial cell takes into account several layers of materials, different materials, and since it's a linear behavior of heat conduction, why do you need to resolve it in that detail? It's just linear. There's no reason for that. Of course, if there's heat source in the center, it behaves differently, but it's mathematically describable. So let's have a look on the velocity. This design point 3 is my coolest, my hottest one. You can see that we have a lot of vortices behind them, a lot of wake. So of course, it's not so much heat conduction, it's just a few pins in here compared to this one, where you have a lot of fins here with so very good conduction into the fluid. Here another one with some streamlines. Or if we want to go into the pressure, you can see here the stagnation pressure on the tips of that, or here how it stagnates in front of all the fins and then reduces slowly over the length of that. Of course, there's some improvement you can make at this point, as well as if you go back to the velocity in this area here, where you have recirculation, you can optimize it, make it not so hard in the expansion, but more slower, or make a fillet in there. So a lot of optimization there you can also do. That's just a very simple example. So I'm not perfect designer in that way. This one here shows the temperature. I didn't put any plots in here because the velocity is mostly defined by, I applied basically a volume flow rate, so the velocity is kind of fixed. We create different pressures. For the temperature here, it's very, very little because we have so high velocity going through. It's 1 liter per second, and the model is from here to here, from the straight line, it's 20 centimeter and 1 centimeter thick, so it's really like through in a second. So the temperatures here are very low. Well, probably reach up to 0.3 Celsius just by passing through from one side to the other. But if we look at the IGBTs now, you can see that with the very coarse distribution of my fins, we have at the beginning where the temperature is low and speed is still high, we have then some stagnation, and this IGBT is hotter also because it sits in between of the two, and therefore is kind of crowded from both sides and can heat up a little bit more. The other one is very good distribution of the fins, so good heat conduction into the whole assembly as well as into the fluid, so better space between the temperature here, better distribution. In this left case, you would probably face some earlier failure in the center IGBT compared to the left and right one, and the other ones, they're equally well loaded with the temperature. And it's not much colder, it's just 6 degrees Celsius colder. You can optimize it, as I said, well, with flow rates. You can also apply a pump curve at the beginning in order to, well, create it more realistic to a pump that you have in front of it. So the pressure changes, the volume flow rate changes, and so on. Now this plot I have to explain a little bit more. We have normalized values, so going from 0 to 1, with 1 just being the highest. We have at the beginning the fin length. It basically says that's 5, we have 15 in the center and 25 in the outer. I didn't change more because we just create more and more projects. The second one is the pin fin thickness. So that's 1 millimeter, 2 millimeter, 3, and 4. Now I colored the lines according to the pin fin thickness, and I dashed and dotted them according to the fin length. So if we go to the lowest one, we see all they start with dotted, the next one are dashed, and the higher ones are then straight full lines, solid lines. The other ones you can see they're all green or all blue from the leaving the point. But what you can see from that is how they influence the IGBT average maximum or diode average maximum temperature, as well as the pressure loss in the model. You can see that it's kept almost constant for the IGBT and diode temperatures in normalized, but also you can see that if we go from green, blue, purple to red, from the size, the dimension, the thickness, from very thick to thin, you can see that the thickest ones, they don't have the good spacing because they would get very thick, so the spacing is wider. So we have larger gaps. So therefore the cooling is not so good. The temperature is much higher. And the next one here, so it goes from top to bottom also. If we compare it to the dashed and dotted lines, you can see very small fin thickness, very short fins cause a very good, very dense distribution. If I go to the further larger one, we have seen before that they get far apart. So that's why the straight lines, if you look at the blue one, the straight line, or the full line, the solid line, is higher in temperature than the dashed line or the dotted line. And that's for all of them. They all have a difference there. So you can see already how each of the parameters that you change influence that not only the temperature, but also the pressure. You can, for example, see for the shortest one and the thinnest one, we have a lot of them. So the temperature is very good, but the pressure increases drastically. So it's the highest pressure loss. If, for example, I say, well, my pump only works in a certain range, maybe or the whole system can cope with a certain pressure loss, unless over that it's just too much. So I can say, okay, maybe the purple one here with the dotted line works best. That's then here the 2 millimeter and thickness and 5 millimeter length. I can also add other parameters if I go into temperature or if I want to change the volume flow rate in order to find out, do I really have to put such a high volume flow rate? Maybe a lower one will still be enough and I can save in pump power that I have to put into the system, especially in electric vehicles where you want to save power. So here you can play with the parameters and try to find the optimum way of doing that. So what we learned from all of that is the CAD-embedded approach that we do with FloEFD. It makes it very easy to work on the CAD model and change all the parameters. That's usually not that easy if you work with traditional CFD tools, especially if the geometry changes completely. You have to remesh it manually often in order to get a good mesh, or you cannot even get to the parameters. You might be able to, change the mesh in terms of stretching it longer, but you're not able to create a round to a square mesh in that way. So here I can just change the dimension, the shape, and everything, and simply rerun it again in the next parametric iteration. The Cartesian mesh is ideal for the automatic meshing. Because first it's very robust for the solver, and the immersed boundary layer model that we use with our partial cell technology makes it able to automatically mesh most complex geometry. So it doesn't matter how the geometry looks. You've seen it's round, it's long, it's stretched, it's closer to each other. We just have to define a certain region over that area and say, okay, just try to fill me up a certain amount of cells within these gaps between two fins, and we'll do that. The parametric study then also can help to find the optimum design. Not the ideal, the perfect design. For that you have to define much finer steps or in order to find maximum values. You just define discrete values to jump from one value to the other, but the perfect design might be in between. So that's where the next step would come in. So you really use an optimization tool, algorithms in order to control that. You check for the temperature. You do it a little bit higher, it gets colder again, maybe in between. So the optimizer really has some algorithm of evolving the different types of that, like ant farm kind of behavior or evolutionary behavior. And that can change then your design. You can manipulate Excel parameters for the CAD model, or even interface into the CAD model, depending on the CAD system that you use. As well as you can log into our API from FloEFD. For example, you can use that already with Mode Frontier. We have an interface directly to them where you can link into our API to control these parameters and change them the way you like or to optimize that.